In this video, we're going to discuss the rate of decay of radioactive materials. And there's a couple ways we tend to think about this. One is the constant of decay. So radioactive decays are first-order decays, which means we can write a first-order reaction equation that says that the natural log of the concentration at time divided by the concentration initial must equal the negative kT. So there's a constant for radioactive decays. And while we can indeed calculate these, a lot of times we don't talk about the constants, we instead talk about the half-life. Half-life is just the time for half material to decay. This tends to be a little bit easier to follow. It doesn't involve as wildly different numbers. You can just say, oh yeah, it takes 10 years for half of it to go away, 20, 3/4 will go away. Because it's always half of whatever you start a time frame with. So if we start with 100 of something, and here's 0, and here at the first half-life, well, we'll have decreased from 100 down to 50. Well, from that point to the next amount of time for a half-life, to the second half-life, we will start with an amount, we will go down to half that amount. Well, if we started with 50, that goes down to 25. By the time we're up to the third half-life, well, from 25, half that's going to be 12.5. And then 6 1/4, and so on and so on. The first half-life sees a larger total number of decay events than the second half-life, because each half-life sees, from whatever amount you start with, half of that amount goes away. As a result, less and less decay events occur over time, less and less radiation is given off. In the event of a nuclear bomb or a contamination event of Chernobyl or 3 Mile Island and the like, the most radiation is in the initial section. This decreases greatly over time as more and more of the material has already decayed. Now, in reality, as your primary radioactive material decays, it may create daughter products that are also radioactive. These may be more or less radioactive, and therefore the total radiation from all sources is more variable. But if you're just watching one material, this is how it decays, and the radiation from that one material will taper off over time. Half-lives can range anywhere from fractions of a second up to billions of years. So less stable isotopes created in particle accelerators and the like have been made. The heavier elements, post-uranium, have been made in various labs with particle accelerators around the world. Some of these last microseconds at best. These can't really be studied, we can't do much chemistry with them, but others that are a little bit more stable, we can do lots of chemistry with. Examples here, let's look at uranium-238 and uranium-235. The half-life for uranium-238 is 4.5 times 10 to the 9 years. So 4.5 billion years, which is about the age of the Earth. Which means any uranium that was on Earth when it began, about half of that has gone away. But that's only for uranium-238. The isotope 235 has a 700 million year half-life, which is significantly shorter. As a result, there's significantly less uranium-235 remaining on the planet than there was when the planet first formed. We can use this to actually solve the K value for both of these decays. Because these are the half-lives, the T1 halves, we can take our formula and we can say, well, the natural log of half of whatever amount I have over the initial one must equal negative K and the half-life. Well, for uranium-235, we know the half-life. 7 times 10 to the 8 years. Rearrange solve for K. The K of uranium-235 is equal to 9.902 times 10 to the minus 10 per year. If you did the same for uranium-238, but plugged in its 4.5 billion years, we'll find that its K value is 1.54 times 10 to the minus 10 per year. So while they're both very small, we see that uranium-235, which decays faster, needs a shorter amount of time for half of it to go away, has a larger K value. Uranium-235's constant of decay is greater, which makes sense for being a faster half-life. Well, we might talk about a half-life of something, but if we wanted to kind of put it into perspective, let's just say we had 1 mole of uranium-235. Let's find average decays per second. In this case, I have a mole of stuff, and I know the half-life. I know that half that mole is going to be gone in 700 million years. So 1/2 times 6.022 times 10 to the 23, and over every 700 million years. Now granted, initially we're going to have a little faster decay. At the last part of that half-life, we're going to be going a little slower. But what's the average over that half-life? Well, in every 1 year, there's 365 days. 1 day, 24 hours, 1 hour, 60 minutes, and 1 minute, 60 seconds. So how many decay events are going to occur per second? If we multiply this out, it's 1.375 times 10 to the 7 per second, or roughly 14 million decays per second. So if you had about 1/4 of a kilogram of uranium-235, 14 million decays per second would be happening. Associated energy is being released. This can do a lot of damage. These are high energy decays that can blast into you, doing damage to various cells and organic components. By no means do you have to damage every single cell at every single point. You just have to do enough to start wearing down the biology. If you ever could hold 1/4 kilogram of uranium-235, you wouldn't be able to do so for long. These half-lives are extremely useful for predicting how long before radiation has decreased to levels where it will be more manageable, but it's also really useful for tracking the age of things in archaeology. Carbon-14 has a roughly 5,000 year half-life. It's a tiny fraction of the carbon in the atmosphere, but it's kept fairly common. Bombardment of nitrogen in the upper atmosphere by cosmic rays causes the nitrogen to convert to carbon-14. This eventually decays, and so there's a input of carbon-14 at a fairly constant rate based on space bombarding the planet. This will build up until you have enough carbon-14 that it's decaying at the same rate as it's being created. So there's a fairly constant carbon-14 on Earth. However, if it gets into a tree, like carbon-14 gets put inside and then it's not able to cycle. If that tree falls over and dies and you just have your tree lying buried under the dirt, it's not getting new carbon-14 from the atmosphere. And so every time one of these decays back into nitrogen, you reduce the number of carbon-14s inside that piece of wood. So we come along some number of years later, we dig it up, we take a sample, and we see that the carbon-14 is decreased from the atmosphere's level down to 12.5%. Well, 1 half-life is 50, 2 half-lives is 25. That'd be 3 half-lives. So approximately 15,000 years prior. So when we go and test stuff from ice ages and the like here in the Pacific Northwest, we dig down, we find remnants of ancient things, we can identify that, oh, this tree was around back during the last ice age. Now this only works out to so many half-lives. Eventually your difference gets down to 6 some, and then 3 some, and then 1 some, and then 0.75 some. Eventually the difference becomes too difficult for our air and our machinery. There's only so many half-lives that carbon-14 is good for. You especially can't go back to the dinosaurs with it. If anybody's ever told you we've carbon dated some dinosaur things, they were wrong. That's not how we test those things. There is radioactive dating we can use that goes that far back. We just need an element with a much longer half-life. Things like uranium, certain xenon isotopes, and the like. And so dating material for when it was isolated and no longer able to freely mix on the planet is a very useful aspect of the decay events for nuclear material.